about 100 years. And in fact, there was only 1 day's warning before this eruption started. There were no seismometers to measure earthquakes nearby. The first earthquakes that people felt was literally 24 hours before the eruption started. In this eruption, it carved a crater in the side of the old volcano, threw ash high up into the atmosphere, and with all this ash moving around, there's a lot of electrical charge, and so you get fantastic thunderstorms associated with the volcanic eruption. And this is a fabulous eruption. Obviously, quite a few people were displaced as a consequence of the eruption, but actually for science it was a very interesting eruption, because these days we can actually watch the volcanoes from space. So this is the weather satellite image in May 2008. You can see the ash cloud blowing across Argentina, and this is now the South Atlantic Ocean. So that's about 500 kilometers across. A couple of days later, you can see the winds change, and the volcanic ash cloud is now moving across a different part of Argentina. And you can see all this pale grey material, that's fine ash that's been deposited onto the land surface. This is the ash column. It's about 15 kilometers high in this case. So it's a very strong eruption with lots of very fine material high up into the atmosphere that then gets blown downwind, again burying people's cars and houses and causing significant disruption, at least for a few months in the region. So ash is the material that tends to be thrown furthest away from volcanoes. And we've got some spectacular records of past eruptions because people have been collecting volcanic ash for hundreds of years. The British explorers in the 1700s and 1800s had admiralty manuals that told them what to record if there was a volcanic eruption. So this is an eruption on Soufriere St. Vincent in the Caribbean in 1812. This is Turner's imagined view of the eruption. And this sample here is about 0.5 millimetre across. This is some volcanic ash that fell on Barbados that was collected in May 1812. This is another sample. St. Vincent erupted in May 1902, just 2 days after the very large eruption of Montpellier, which is the neighbouring island. And again, people were busy collecting ash samples that they fell on Barbados in this case. These slides, this is 1 millimetre across, and you can see these are actually crystals, probably of pyroxene and plagioclase felspar. These are crystals that have been blown out from the volcano during the explosive eruption. Of course, in the UK, we know all about volcanic ash now, ever since the eruption of the Eyjafjallajökull eruption in Iceland in the middle of April 2010. So this is again, a weather satellite image. You can see the trail of ash from the eruption blowing off Iceland and then off towards, in this case, Norway. Now, the Icelandic eruption was a very interesting one. It had about a month when there was a lot of violent fire fountaining at the volcano, but there was no particular ash formation. Then the eruption then stopped for a day, and the location of the eruption moved from the side of the volcano to the summit of the volcano. Now, the summit of the volcano had a big crater that was filled with ice, probably 100 to 200 meters thickness of ice, and the molten rock that came into the summit region was actually much stickier than this very fluid hot lava on the sides. So when the sticky magma came up underneath the ice, the heat from the magma started to melt the ice, the temperature drop caused the magma to break up, and then the contact of water with the magma meant that you got boiling and steam production. So here we've got a very violent phase of the eruption, with lots of steam, the pure white cloud, and also lots of ash, which is the grey cloud in this case. A year later, there was another much larger eruption in Iceland, the volcano Grímsvötn. This also erupted through an ice cap. In this case, it was a very fluid magma. It was a very energetic eruption, and most of this eruption was actually driven by the expansion of gas bubbles inside the magma, rather than there was a little bit of melting of ice, but there wasn't much in the way of there wasn't as much contact between the hot magma and the ice as there was in the case where we had the sticky magma sitting underneath this pool of ice in the crater. And if we look at the magnified images of these samples, again, this is under a scanning electron microscope. In the case of the Icelandic eruption of April 2010, the one that produced all the ash, you see that the fragments just look like blocks of broken rock. They're sort of angular. There's no bubbles in this material. So this is hot magma that simply shattered. This is the Icelandic eruption from a year later, and here you can see the curved edges that used to be the edges of bubbles. It's 10 microns. So again, the width of a human hair would be about this sort of size. So by looking at what comes out of volcanoes, you can learn something about how the eruption happened. And of course, we did get volcanic ash in Britain. This is now a very highly magnified sample. These small particles here are all volcanic ash particles that landed in Oxford. These crystals here, these are sulfate crystals that had actually grown on the filter paper as we were collecting the samples. This is a sample from somebody's car windscreen in Derbyshire. And in fact, people everywhere noticed there was an accumulation of grime on surfaces during the eruption. But in fact, it was actually a high pressure system. There was a lot of pollen production. So in fact, most of these grains, these rounded grains, these are all pollen grains on the car windscreen. And the volcanic ash is this little cluster down here. So not much ash got to the UK, but we can just about find it. Those were tiny eruptions, though. The largest eruption that we know of the last 20 years or so was the eruption of Mount Pinatubo in the Philippines in 1991. And this threw up an ash cloud that reached about 25 kilometers high in the atmosphere. In this case, if we look at the rock that was erupted, this is a magnified image, and these things here, these are crystals of a mineral called hornblende or amphibole, and these are minerals of a crystal called plagioclase. Now, this mineral here, hornblende, is only stable in magma that contains a lot of dissolved water. So 4 or 5 kilometers beneath the volcano, the magma was very, very wet, with lots of dissolved water in it. And then as the eruption started, that magma rose up, the pressure dropped, the water all boiled out of the magma, just as you saw with the kind of Coke bomb experiment. And that drove the energetics of the eruption. Ash was a significant problem in this case. This is an aircraft 40 kilometers away from the volcano that was obviously grounded by volcanic ash. And it's those very large eruptions, Pinatubo was one example, Krakatoa was another example, that can then have a global effect because of the fine particles that form in the atmosphere following the eruption. This is an image, it's from November 1883. It's about 3 months after the Krakatoa eruption. So in the 3 months that have followed, basically all of the ash from Krakatoa has now settled out of the atmosphere, but Krakatoa also released sulfur into the atmosphere, probably at 20 to 25 kilometers height. And that sulfur gradually, slowly reacted to form droplets of sulfuric acid, tiny droplets, kind of a micron size. And those droplets have now spread all the way around the globe. And as the sun sets, you then get a lot of scattering of sunlight, which then gives you very vivid sunsets. As well as ash, many volcanoes also release gas. So this is Stromboli volcano, which is losing gas out of about 7 craters in this case. And volcanologists use various bits of kit. This is a spectrometer, and it's actually looking at this hazy plume over here, which is a gas plume coming off a volcano in the Caribbean. This is my favourite volcano, the first volcano that I visited when I was 7, and it's here again. You can see it's sort of gently puffing gas out of the top. It's a lovely volcano because you hike right to the top here into the crater where there's a bubbling lava pond, and again, gas streaming out of the volcano. And if you collect samples of that gas onto filter papers, actually some of these volcanoes produce the most fantastic little spherical droplets. These are just little droplets of silica. We're not quite sure how they're produced. And you can find droplets even down to the size that you would call nanoparticles. Now, most of the world's volcanoes erupt quite sticky magma, and the main constituent of that magma is silica. But the world's strangest volcano is this volcano in Tanzania called Old Onyo Lengai. It means the mountain of God. This is an air photo of the summit crater in 1993, and this crater, you can see it's, maybe can't really see the colours there, but if you walk into the crater, this is a freshly erupting lava flow. It's kind of a deep brown colour, and these old lavas are actually a paler brown colour, and even older lavas are now sort of white. This volcano erupts in just the same way as any other sort of volcano. So you can see fumes of steam and ash cloud coming off a little summit cone. It's just that it's made of sodium carbonate.